Okay, problem number 1E. You might be looking at this and being like, what on earth is this? Well, remember we talked about these functions back in Unit 3 when we discussed limits. This is a logistic curve. Generally speaking, they look like that. They have a horizontal asymptote up there at some level, and they also have a secondary horizontal asymptote down there. To the left, they level out to 0, and to the right, they level out to some value, which we call a carrying capacity, because this is the type of function that you can often use to model populations of animals, for example. So if you think about the y-intercept of this function, that would be like saying t equals 0, and i.e. that would be the starting population of some ecosystem or some animal in an ecosystem or something. So let's figure out some things about these functions. If you remember why we talked about these in the limit unit, it's because we can determine the carrying capacity of this function by analyzing the limit as x goes to infinity. So let's think about the limit as x goes to infinity. That's not a very good infinity symbol. Limit as x goes to infinity of this function, 140 over 7 plus 7e to the negative 0.2x. And if you think about it, this term right here is the only term that has an x in it. So if we can figure out what that term does, we can figure out what this function does. So let's think secondly about the limit as x goes to infinity of just this term, e to the negative 0.2x. Well, as x goes to the infinity, we get e to the negative 0.2 times infinity. We're not really multiplying by infinity, we're just kind of thinking about this conceptually. So think of infinity as like a really big number. So negative 0.2 times infinity is like e to the negative infinity. Infinity, you can kind of think of it as like absorbing that 0.2 because it is so gosh darn big. But it is negative, so it's going to take that. E to the negative infinity is like saying 1 over e to the infinity. And e to the infinity is infinity, so this is like saying 1 over infinity, which is like saying 0, because we have a really big number in the denominator. So this whole term, e to the negative 0.2x, goes to 0. So we get 7 times 0 right there. 7 times 0 is 0. So this term goes away. And we just get 140 divided by 7. And think of 14 divided by 7 is 2, but it was 140, not 14, so add that 0 back. So we know that the limiting size of this population, i.e. the carrying capacity, is 20. And we want to figure out that y-intercept there. Well, the y-intercept occurs when x is 0. So let's plug 0 into this function. Y equals 140 divided by 7 plus 7e. We have negative 0.2 times 0. So that's going to make this whole exponent 0. E to the 0 is 1. 7 times 1 is 1. So in the denominator here I get 7 plus 7 is 14. So this simplifies to 140 divided by 14, which is 10. And so the starting size of the population was 10. The domain of this function is all real numbers. When we're thinking of the function in general, not really when we're talking about the population, but the range of this function is going to be y values that are greater than 0, but less than 20. So let's graph all this together now. I'm going to say 5, 10, 15, 20, going by 5s there. I'm going to plot myself a y-intercept, and I'm going to sketch in this curve. And I misspoke because the y-intercept should be at 10. So I guess I'm going by 2.5s, and I need to go up another set of those to get that horizontal asymptote at 10. So this is 20, I misspoke again, and that is 10. And this checks out. That is what this function is going to look like. Notice I don't have a scale on my x because I'm not really sure how steeply it goes. I can't really graph that accurately, so I'm going to unlabel it. But I do know that those two specific values are indeed there. All right, one last graph here, 1f, another logistic curve. Domain of this function still going to be all real numbers. I can plug any x value into that function and it will work. Range, I need to figure out first by determining what the carrying capacity is, i.e. the upper horizontal asymptote. And remember how that worked before. It ended up being this numerator divided by that first term of the denominator, because the limit as x goes to infinity of this term is 0, so it went away. So I get 990 divided by 11. Well, think of 99 divided by 11 is 9, but I have that 0 there. So the carrying capacity is 90 right there. So that tells me that my range is 0 is less than y is less than 90. You could also say 0 to 90 like that. Starting population here, i.e. y-intercept, plug in 0, and we end up with then just this, 990 divided by 11 plus 88, because that term goes to 1. And so 11 plus 88 is 99, so I have 990 divided by 99, so I get a starting population of 10. And so I'm going to sketch all this in 1, 2, 3, 4, 5, 6, 7, 8, 9. My scale is going to go by tens, so this is 90 up here, and that's 10. And my graph is going to come in and go up, level out, and I'm going to have that horizontal asymptote right there. So that's kind of sloppy looking, but that's generally speaking what we're looking for with this.